Today I'm going to show you a lab that we set up to show the magnetic field on a current carrying wire. Let me show you the setup. We have the Pasco variable gap magnet. With these things right here, you can twist them and you can make it go in and out so that you can change the strength of the magnetic field and actually, just the gap. But the closer they are, the stronger the magnetic field. You'll notice right there that there's blue on the end of that. That's painter's tape, because the end of magnets, the magnets tend to be very easy to chip, and that's something that won't leave a residue on the magnets, but it's a way I can do different demonstrations, and it doesn't change the magnetic field. This right here for me is the wire that we're going to use. Notice that I try to make it as perpendicular to the magnetic field as possible. The whole setup from out here, notice I just used a group of rods with the 90-degree clamps, and I can change the height of the variable gap magnet. Then I go from a power supply that's variable, I hook it up to one side and then the other, so that the current is going to be going this direction. And then if you'll notice over here, the final piece goes through an ammeter. I have this ammeter set up to 10 amps. This thing right here says a maximum of 5 amps. We eventually actually only get about a little over 3 amps from it. Okay, turning on the scale, and that will go through its preparation here. Okay, now notice it says 0. I'm going to turn on the ammeter to 10 amps. Because if you don't do 10 amps, you'll have too much current running through that. And try to get that to where you can see it without, there we go. And then I'm going to turn on the power supply, starting at 0. Okay, I have it on DC. And watch what happens as I increase. Let me go ahead and 0 that. So watch what happens as I increase the current running through that wire. It shows negative. Well, what does negative mean? Negative means, notice the current is going up and there's some sort of force occurring here. Let me show you what that actually means. I'm going to put that down to 0. If I push down on this, it reads positive. If I lift up on it, it reads negative, which means that the force on the wire is actually up. You can actually do the right-hand rule because the current's flowing towards me, so that would be my thumb, that the force is upward, so that means that the magnetic field must be going that direction. Okay, now again, watch what happens as I up the current. The current goes up and the magnitude of the force increases. In the next video, I'm going to give you data that we took earlier. We try to get right on good numbers here, and I'm going to give you the data that we took and a little bit of the background on what you should be doing in order to actually make this into a lab. Alright, here's the data that we took in the lab earlier. Notice this over here is in grams. This was from the scale. And this actually gives us the magnitude of the force, but again the scale reads in grams, it does not read in newtons. And this was the ammeter. This was the multimeter. Now you should be able to remember from your magnetism equations that one of your equations, I call it Fabil, it's the easy way to remember it, that we have a magnetic force created by a current going through a wire of length L in a magnetic field of magnitude B. This is in Teslas, amps, and meters. Just by the way, we actually read this and we got this to be 2.5 centimeters. You should know how to change that to whatever it should be to be in this equation. The force will come from this. The scale reads grams, but you need to convert that to newtons. So I'm going to give you a few minutes. I'm going to pause this and you need to figure out how to change that to force. And you are going to graph this. You are going to have one of these on the x-axis, one of these on the y-axis, and you need to figure out which ones those are. Remember, one of the rules that we use, there are two things to think about. One, we often do the x-axis as the manipulated, and the y-axis as the responsive. In other words, what responds to what you manipulated. Now the other thing that we have to think about, we'd sure like this to be some sort of straight line so that we can find the slope. And slope is always delta y over delta x. So here's the conflict. Usually you would put your manipulated here and your responsive here, just as a matter of practice. But you would also like the slope of this line, you would like the slope of this graph to give you something useful here. And what are we looking for? We would like to find the magnetic field of those magnets. So I'll pause here and let you deal with that for a bit. So let's find out if you did it correctly. You should have figured out that our responsive variable, what we changed was the current. So this will be in amps down here. And there's your amps going from 0.25 all the way up to about 3.5. This over here is going to be the force, because the force varied, the force responded to the change in amps. Now, how are you going to calculate force? Well, we know that F equals ma, and we know the force of weight equals mass times the acceleration due to gravity. Well, this mass has to be in kilograms. So your force of weight, the force that we actually got, will be in kilograms. So we're going to have to take our grams, divide by 1,000, then multiply it by 9.8. Let's just double check that we understand why that is. Remember that there's 1,000 grams in 1 kilogram. So if you're given grams, divide by 1,000 and you get kilograms. So you need to take all of these numbers, and in another part of your data table, you need to get me the weight of this object by doing your calculations. I will pause. Oh, and then you need to set up your graph. Let's see how you did. So this should be your x values here, because remember, those are amps are manipulated. These will be your y values. Now when graphing this, notice these are pretty small numbers. So you're not going to put something and say, well, this is 1, and you're going to break it up. Instead, you know, this is almost 0.004, so maybe I would work and say that my force on this side, I would just say that this is in, you know, times 10 to the minus 3 newtons. Or millinewtons if you want to work it that way. And your amps, looks like amps, I'm just going to work flat out in amps because that's going to be pretty easy. So you're going to want to go ahead and graph this. And oh, by the way, when you finally get your graph and you're going to find your slope, what does that slope actually mean? Well, y divided by x, force divided by amps, which is going to be I. I should have done that. So force divided by I does not give me the magnetic field. It actually gives me in units of Tesla meters. But remember, we already found out that this is 0.025 meters because it was 2.5 centimeters. We measured that with a ruler. So graph this. Knowing this number, you should get me a value for B. Let's do this now in Excel and show you how I would do this. I'm going to insert a graph, a chart, and for some reason we always use a scatter graph. Why that is, I'm not totally sure, but next, and I'm just going to finish. Now you see there's nothing in that graph, and you'll go, well, that's not very useful. However, we're going to put data into it, show you how to do that, so you can actually put multiple things into the same graph. So I'm going to do source data, I'm going to do series, and I'm going to add a series. Now this new series that I'm going to do, I'm going to call it force versus current. And then my x values are going to be my current. Yes, this is a lot easier than what you did on paper, but again, you know, in college they'll expect you to be able to do things like this. Okay, that's a pretty nice little straight line, isn't it? Well, let's get the slope of it. I'm going to add a trend line. Options. We do know that the y-intercept is 0. Why? Well, when we turned off the electricity, there was no force. We zeroed it out at that point. Then we're going to display the equation. Okay, and there's our equation, 0.0175. I don't know why it keeps that color. I know I can get rid of that color. Maybe that makes me happier. And this I actually don't need, since we only have one thing on this graph, so that's not too bad. Now we should put a chart title and call that force versus current, and then we should put units and so forth, but we're not going to do that just for speed here. Now, but what about the actual magnetic field on the, what is the actual magnetic field? Well, let me go ahead and let's just do this. So we know our slope equals 0.175. Did I write that correctly? I did. And we actually found out that that's in Tesla meters. That's not in Teslas, which is what we're looking for. Well, we know that our length equals 0.025 meters, and we actually want Teslas, so Tesla meters divided by meters gives me Teslas, so I'm going to divide by the length. So B is going to equal this number, I'm going to do this, equals this number divided by this number, and gives me 0.7 Teslas. Now, a Tesla is actually a really big unit. The magnetic field of the Earth is quite small. And so I was actually quite surprised when I saw this number for 0.7, but then I checked with Pasco, and it says that those magnets have up to a 1 Tesla field. So we did pretty well. And now that may mean that those magnets, if they get even closer together, have a stronger field. There could be other issues going on here, but we're going to say that that's in the right range.